Leaving this integral up here just for reference. Remember, this is a volume integral for the sphere centered at 0, 0, 1, resting basically on the origin of the XYZ plane and sitting on the XY plane. Okay. We want to find the center of mass of this region in the Y direction. Remember, we also had a density function. Density equals 1 plus Y. So what we want to do is just to understand what we mean by the center of mass. I'm going to imagine partitioning the Y-axis. And I'm going to draw the contour lines along the surface. Now what I've got is the intersection of the surface with the YZ plane, the intersection with the XZ plane. Slices parallel to the Y-axis are going to look something like this. Okay, not very well drawn, but hopefully you get the idea. Why do I do Y slices? Well, remember we have our density function. Now, density is a function of x, y, z in general, but this function just happens to be 1 plus y. So to visualize what happens to the density, or what happens to the mass as we move from left to right, we can visualize these slices. Now, if the y intervals are uniform, we have more volume in the first several slices than we do in the slices over toward this extreme. However, density being 1 plus y, when y equals 0, the density is only 1. When y equals 1, the density goes up to 2. So we have less density on this end, greater density on this end. Now we imagine that gravity is pulling each of these disks, or quarter disks or half disks, down, tending to rotate the solid about the x-axis. If we draw just the y-axis here, the interval from 0 to 1, and imagine that we have some kind of a fulcrum here, we can see that a front view of this quarter of a sphere might look like this, again with our y slices. If we want to look at our mass distribution, okay, the mass of the second slice is probably greater than the mass of the first slice, because the second slice isn't that much smaller, but the density is somewhat bigger. And the masses of these slices are going to go up and up as the density goes up, and the volume doesn't shrink all that much. Now eventually the volume is going to shrink fast enough that the increasing density doesn't keep up, so that the densities of these slices will, or the total mass of these slices will start to fall off. We could sketch a graph here just representing how much mass is in each slice. Looks like we're going to get a little more mass in the second slice, the third slice, and maybe even just a little more here. But now the diameter of these slices is starting to decrease, and the mass in each slice is going to decrease accordingly, so that by the time we get out here we don't have much mass. If we visualize this as a massless support supporting all these masses with a fulcrum right here, we see that we get a torque from each slice, a moment tending to rotate the quarter sphere, or the half, no, it's a quarter sphere, the quarter sphere around this fulcrum. The tendency to rotate we'll call that torque, with a few apologies to physics. The tendency of this thing to rotate is going to depend on the mass in each slice and the position of the slice relative to the fulcrum. The further a mass is from the fulcrum, the more it's going to tend to rotate, but if there's less mass, then there'll be less tendency to rotate. And the tendency of one slice to rotate, the torque or moment of a slice, is how far it is from the x-axis, which is distance y, or let's say y sub I star. Actually, since we tend to use j for y, we'll call it y sub j star, multiplied by how much mass. So that would be a y sub j star times the amount of mass in the jth interval. Now, the mass in the jth interval consists of the contributions to the mass within the given j interval, within the given j subinterval, which itself consists of a bunch of delta x by delta z volume increments. And I'll say then that the tendency of the mass in a volume increment and let's call that the rotational tendency of the mass in a volume increment relative to the x-axis, where we consider the fulcrum to be actually at the origin, but the gravity to be pulling straight down so that the rotation is about the x-axis, is then simply y sub j star times the mass in that increment, well, the mass in that volume increment. And the mass in that volume increment is nothing but the density at our sample point within the increment times delta x, delta y, delta z. Summed up over all the volume increments, we follow the usual procedure. If we follow the usual procedure, we'll get the triple integral of y times delta of x, y, z. We'll go in the same order as before, dz, dy, dx, where we're integrating over the same region that we integrated over which we integrated originally. So that region we should be familiar with goes from 0 to 1 with respect to x, from 0 to the square root of 1 minus x squared with respect to y,